Okay, so this is a continuation of chapter 11 of Giancoli 6th edition. So we already saw about this simple harmonic motions. We talked about these motions having no friction, so keep going back and forth in the case of the spring, in the case of the pendulum moving back and forth forever. But this is not realistic. We know in nature there is friction, so what we get is the damping of those oscillations. So this is what you see in this plot here. Now we started with a certain amplitude here, but you see that this amplitude is slowly decreasing. So this is what we call the damped harmonic motion. And this envelope of the decay of the oscillations tells us how this amplitude is decreasing. Now, damping is not always bad. It is bad if you think, for example, of a clock. Now you have to go on and turn it again so it keeps moving. You know, those big old clocks that your grandparents may have. But it may also be a good thing. A good thing is, for example, those springs that we have in a car, the shock absorbers, right? If we didn't have any damping, we would keep moving back and up and down on the car for a long time whenever we would hit a hole. And it's also good for buildings and bridges. You know, they all have springs to try to damp the oscillations in the case of strong winds or in the case of earthquakes. Very good. So in general, in reality, we'd have these damped harmonic motions. Okay, to keep things going, what we usually do is to add uh, energy to the system. And we do that by applying a force, for example, periodic driving force. And to keep these vibrations, these motions going. Now, there are some interesting things about applying these external forces. If we do that, if this this periodic driving force has the same frequency, has the same frequency as the natural frequency of the object that we are playing with, then what happens is that the amplitude is gradually increasing. So the idea is, think about when you go to the playground with a child, right? And you periodically pushing this child and you see the amplitude getting larger and larger because you're applying this external force with the same frequency, with the same period that the swing has. If you do that in certain cases, for example, if you pick a glass of wine, well, what we have there are the molecules vibrating, and they have their own frequency, the natural frequency. If you scream close to that glass, if you start singing close to that glass, but with the same exact frequency as the molecules have, what will happen is that the amplitudes of the motion of those molecules will increase, and you may even be able to break the glass. And if you search at YouTube, you will find some examples of that. It's quite impressive. But what I really want you to watch is this movie about the Tacoma Bridge. This is a real fact of a bridge that broke because the winds were blown with the same frequency, with the same natural frequency of the bridge, and the bridge collapsed. So I really want you to watch this video, and I'll have some questions for you about this video in the quiz. This is the questions will be very simple. I just want to be sure that you watched. Okay, no many details about the numbers and things like this that they give us in the bridge. Some simple questions about the bridge just to be sure that you watched. I'm sure you're going to like it. Okay, now let's continue. We said that in this chapter 11, our purpose was to talk about oscillations, vibrations, and then use these oscillations to create a wave. So that's the second part, is to create these waves and describe these waves. Okay, so here at the bottom, what we have is someone applied a jerk, no, a pulse on this rope. And you see, so it's just the hand just went up and down fast. So, and then you see that this pulse goes on propagating to the right. So this is the idea of the wave. See, the particles of this rope, they only move up and down. They do not move to the right, but I see something moving to the right. I see this crest moving to the right. So what is this crest? It's the energy. Okay, the energy is moving to the right, while the matter, the particles of the rope, are just moving up and down. Okay, so this is very important about waves. Waves carry energy from one place to the other, okay, but they do not carry matter. So I have the particles moving up and down, but what is moving to the right is this crest, is the energy that I injected into this rope. Okay, okay, so this was just the pulse. But I can keep moving up and down, up and down, up and down, and create a whole continuous wave. And if I move up and down with a simple harmonic motion, the wave that I create is a sinusoidal wave. No, it has this sinusoidal shape. Okay, so that's the point. Everything that we saw up to now, these simple harmonic motions to describe the oscillations, to describe this vibration, was then to be able to create now a wave with this sinusoidal shape. Okay, let's move on. Some definitions now. Here we have our sinusoidal wave, that has this sinusoidal shape, and I want to define some quantities. The first one is what we call the amplitude of the wave, and the amplitude is the maximum displacement up or down of these particles. Okay, so this maximum height for the crest or this maximum depth for the trout. So this is the amplitude. Very well. What else do I have? The other quantity that we define is the wavelength. So the wavelength is the distance between two crests, or is the distance between two equal points, also the distance between two troughs. You see here, this is the wavelength, this is the wavelength, and the letter we use to describe this wavelength is lambda, the Greek letter lambda. But I could pick any 2 points. For example, I could pick this point here. And where should I go to get to count the wavelength? Well, I have to go all the way here. Okay, I cannot stop there. You're going to say, well, but this is point 0 and this is point 0 also. Well, but here I did not complete a whole wave. I have to have trough and crest and then go back. Okay, so I can also measure the wavelength between these 2 points here, but from this point all the way to that. Okay, I have to cover the whole wave to be able to count, to talk about a wavelength. Okay, and we also have period and frequency. So what is the period? Is the time that that passes between two crests. So it's the time that it takes for the energy to go from this crest all the way to this other crest. Okay, or in other words, it's the time that it takes for this crest to go down, become a trough, and then come back to crest. This is the period. Okay, or as I said, is the time that it takes for the energy to go from this crest all the way to the other crest. And what is the frequency? I pick any point here and count how many crests I get at that point in 1 second. And then finally, what is the wave velocity? And what is the velocity of the propagation of this energy? Well, the wave velocity is velocity that it takes for the energy to go from one crest to the other. And I know that the time that it takes to go from one crest to the other is the period. So with that, I say that the velocity, the wave velocity, is the wavelength, because this is the distance between two crests, divided by the time that it takes to go from one crest to the other. Okay, so this equation here is the velocity of the wave, the wave velocity. And this is analogous to what we are very well familiar with, delta x divided by delta t. Right? The delta x here is the distance between two crests, and the time here is the time that it takes to go from one crest to the other. All right, let's continue. What we are going to do now is we are going to solve a problem, but let's use this equation that we have, that the velocity is the wavelength divided by the period. Can also write that this velocity is the wavelength multiplied by the frequency. 1 over period is the frequency. Now there is another equation showing up here for, again, the speed of the wave, but it's an equation that is coming from nowhere. We are not going to derive this equation, so this is one of the few equations that you do not need to know. It will be given to you in exams and in problems to solve. Okay, so you do not need to know this equation. You don't need to know You don't need to memorize this equation, will be given to you, but you need to know how to use. Let's try to get just some intuition about this equation. What this is telling us, that the speed of the wave increases with the tension. This is the tension force that we find on the rope. Okay, so the more tense this rope is, the easier it is for the different particles to communicate. They are really tense, they're really together. Okay, so that's trying to give an intuition why the speed increases with the tension. Now, what is showing up down here? Mass divided by length, the length of the rope. Mass divided by length, I can say that this is density. You're going to say, oh no, but we learned that density was mass divided by volume. Yeah, this is true. But since here I have just a rope, it's almost a one-dimensional thing. So I can, instead of writing the volume, use the length of this rope. Okay, so that's why I'm saying that what I find in this equation is the tension force divided by the density of this rope. And again, trying to give you an intuition, when this rope is really, really dense, it's hard to make these particles move. So it's a heavy thing that it's hard to make it move up and down. So that's why the speed is proportional to the tension force. Tension force helps, and inversely proportional to the density. Okay, but there is also the square root. So since we didn't derive this equation will be given to you whenever we have to solve a problem. Okay, so then we have here a problem to solve. And what is the problem? I have a wave whose wavelength, so let's put the data that we have here. Let's erase what we have here. Okay, so they gave us the wavelength. So the lambda is given to us. So let's write this down. The wavelength is 0.30 meters and is traveling down a 300-meter long wire. Okay, so we have also the length, 300 meter. And the total mass of this rope, of this wire, is given to us 15 kilograms. If the wire is under tension, and this tension is 1000 newtons, okay, so I'm going to put here, the tension is 1000 newtons, then comes the question, what are the speed and the frequency of this wave? So we want to know the speed, V, and then the frequency. Okay, for the speed, look, they gave us tension, mass, and length. So we can just go for this equation here. And so to find the speed, I just use square root of tension force divided by mass divided by L, divided by this density. Okay, so use this equation to find the speed, 140 meters per second. Once I have this speed, well, they ask me the frequency. Okay, so then I can use the equation for the wave velocity, which is wavelength multiplied by frequency. I have the speed, I just obtained it. I have the wavelength, it's 0.30, it's given to us here. So then we can find the frequency. Okay? Okay, so this is the continuation of the chapter 11. We just finished this problem 11:11, this example from the book. There is a comment here that I think is important for you to see, which says that the wave velocity is different from the velocity of a particle in the medium. In other words, the velocity of the energy that is being transferred through this rope, for example, is not necessarily the same as the velocity of the hand that was moving up and down to create the wave. Okay, so these two things are different. The wave velocity, the velocity of the energy, is not necessarily the same as the velocity of the particles moving up and down. Okay, now let's move to the next slide, slide 17. And what we have here is definitions. What the different kinds of waves. We just talked about a transverse wave. Okay, the hand that was moving up and down here and creating this wave with this sinusoidal shape. This kind of wave is called transverse because the hand moves up and down. Okay, so each particle here just moves up and down, but the energy, the wave, the crest is propagating to the right, so perpendicular to the motion of the particles. So that's what we call transverse. Okay? But there are other kinds of waves. Another kind is the longitudinal wave. That's what we are doing here. You see, this person has a spring, and what she's doing is she's just moving a little bit to the right and to the left. No, so she has this continuous motion, right, left, and this creates a wave in the sense that these compressions and expansion regions are propagating to the right. Okay, this kind of wave where the particles move up, don't move up and down, but move right and left, short motions right and left. At the same time, the wave also propagates to the right, no? So they are in the same direction, the motion of the particles and the motion of the waves, they are called longitudinal. But careful, right? The particles here, a particle here next to the fingers, do not move all the way there, right? What goes all the way to the right is just the energy. The particles by themselves just move a little bit around its own region. Okay, very important kinds of longitudinal waves are the sound waves. And that this in this drawing here with the drums, that's what we have. You see, when we are hitting the drum, what happens is that that membrane of the drum extends and compresses, extends and compresses. And what happens to the air around it? Well, when it extends, the air gets squeezed together. All these molecules of air have a little space, so they get compressed. When the membrane gets compressed like this, then the air around has more space, it gets expanded. So we end up creating these regions of compression, expansion, that propagates to the right. This is the sound wave that will hit our ears and we'll finally listen to it, now hear the sound. Okay, so we have this oscillatory motion of the membrane that creates a sound wave that propagates through the medium. The medium in this case is air. All right, so some details about waves. What we are doing here is we have a pulse. Now we create a pulse, and we want to see what happens to this pulse when it reaches the end of the rope. Okay, well, what is going to happen will depend whether this end, this extreme, this edge of the rope is fixed, cannot move, or is free to move. Okay, so when it's not move, when it's fixed, cannot move, there is a nail there. What happens is the crest, this pulse is coming. When it hits the nail, it tries to bring the nail up, it cannot. So it tries to bring the nail up, the nail reacts and pushes the wave down. So this pulse down. So what we see is this pulse coming back, inverted. Okay. But on the other hand, when this edge is free to move, what happens is, okay, the pulse comes, brings this edge of the rope all the way up, and then it comes down, and then we see the pulse being reflected, and again with the same still upright. Okay, so it gets inverted if this nail is there, if the edge of the rope cannot move, so from up it goes down, while it just comes back upright when it's free to move. Now, a combination of these two ideas we see here when we have a rope, but with different densities. So this is a very light, dense, not dense at all, very light section of the rope, and here's the very heavy section, very dense. So what happens? Well, when the pulse comes from this light section and finds the heavy one works partially as a nail, so part of it gets reflected but inverted, and the other part just moves a little bit up and we get a transmitted pulse. No? So it's a mixture of two things. Okay, now let's continue with this idea. And what we are going to be doing is, instead of just having a pulse like this, we are going to have a continuous wave. Okay, we have a continuous wave propagating to the right and another continuous wave propagating to the left. And when they meet, we want to know what happens. If they are completely in phase, they are tuned. No? So when they are in phase, what happens is, well, the crests of one coincide with the crests of the other, and we have a constructive interference And so this wave just gets the combination of these two waves just gives us a new wave with a bigger amplitude. On the other hand, like in this drawing here, where they're completely out of phase, the crest of one coincides exactly with the trough of the other, then when they get together, we have this destructive interference. And here in part C, we have a combination of these two. Now, it's an intermediate scenario where I don't have complete destructive interference, nor I have completely destructive nor constructive interference, something in between. Now let's see what we are going to do with these ideas, okay? Let me show you the drawing. What we have here is at the edge here, the rope is fixed, so I'll call this a node. This is a point that cannot move up or down, so it's a node, okay? And here I'm going to move this rope up and down. What is going to happen? Well, I have waves propagating to the right, getting reflected by this wall, and then coming back to the left. So I have this combination of waves moving to the right and to the left, interfering, and let's see what we get. If I hit the right frequency, I get what is known as standing wave. What is a standing wave? It's a wave that doesn't seem to be propagating. What we have here is just these up and down motions, okay? I don't have the feeling of the propagation of the wave to the right or to the left. It looks like it's as if it was standing, as if it was fixed there, just going up and down. So this is what we call a standing wave. It doesn't look to be propagating because I have this complicated interference between waves going to the right and to the left that gives us this sensation. Now, depending on the frequency, we get different shapes of these standing waves. This first one that we are seeing here, where I have just this node at the edge, this one is called the first harmonic, and we'll talk more about it. But as we increase the frequency, you see new nodes showing up in the middle of between my hand and that edge. Okay, so the higher the frequency, the more nodes we get. Okay, so we have these nodes that are completely not moving, they are not going up and down, and the rest of the wave seems not to be propagating. It seems only to be, each point seems just to be going up and down. I don't get that sense of a crest propagating to the right. Okay, so these are this is the basic idea of standing waves. The higher the frequency, the more nodes we get. Before we continue, what we are going to do now is try to get equations for these standing waves. But before we continue, I would like you to stop here and watch two videos that I put for you in Canvas that illustrates these standing waves. Okay, the first one is very short but very good, very instructive. The other one is a little longer. You don't need to watch the whole thing, but just see movies about these standing waves before we continue. So stop here, watch the movies, and then we move to the next slide. Okay, so if you already watched the movie, I'm going to the next slide. What I want to do here is I want to find equations to describe these standing waves. Okay, so here on the top, I have this wave fixed at both edges. You could think, for example, this is the string of a guitar, for example, now where both edges are fixed. And I'm going to start moving this rope with a certain frequency. Okay, so I'll be creating, if I hit the right frequency, I'll be creating these standing waves that we talked about. Now, so here, low frequency, I just have the edges being fixed, being nodes. Here, a higher frequency, so I have one extra node in the middle. Even higher frequency, so now I have two extra nodes in the middle. Okay, you saw the movie, so you know that this whole thing is moving up and down, and that we don't get the sense of something moving to the right. That's why we are calling this standing waves. What we want now is to give equations for what we are seeing here. Okay, so let's see. This first one, where we do not have any node in between, we just have the nodes at the edge. This first one is low frequency, is called the first harmonic. Okay, people who study music may be more familiar with these words, right? So this is called the first harmonic. I increase the frequency, I create now a node in the middle, and this becomes known as the second harmonic. Increase even more the frequency, now I have two nodes, and this is known as the third harmonic. And we can keep going, fourth harmonic, fifth harmonic, and so on. Okay. There are also different names for that, which is a bit confusing, but so first, second, third, fourth harmonic, and so on. Or you can say that this first one, the lowest frequency, is the fundamental. That's another possible name for the first harmonic. And if you use this word fundamental, you say now that the first one on top of this fundamental, which is the one where I have a single node in the middle, becomes known as first overtone. And if I increase the frequency and now I have not just one node in the middle but two, then this becomes known as the second overtone. Okay, so it's a matter of preference. Either you go first, second, third, fourth, fifth, and so on harmonic, or you go fundamental, first overtone, second overtone, third overtone, and so on. It's just a name. But now let's go for the equations. So in this very low frequency that we had here, we created this standing wave, and what do we see? Look, I have a node here. I go through a crest, okay, and I come back to the node. I cannot even, with this low frequency, I don't even create a whole wavelength, okay? So this L that you see showing up here is the length of the total of the whole rope, okay? And what we see is that with this low frequency, I have not even create a whole wavelength, the shape of a whole wavelength. So I'm going to say that with this L, I got just half of a wavelength, okay? This is the equation that we are going to write. Now, you see this little index that is showing up 1 here. This is just to tell us, well, this is the first harmonic, okay? Nothing else besides that. Okay, let me improve this drawing a little bit. It shifted a little like this. Okay, now let's see the next one. The next one is, what do we have is, we do see a whole wave showing up. So I'm going to say that with this whole length, the whole length of the rope, I created a whole wavelength. And I'm putting this index 2 here to remind myself this is the case where I have the second harmonic. And finally, in this last case here, what we have is with this whole length of the rope, I created one wavelength, right? You see it completely here, crest and trough, so a whole wavelength plus half of the next one, no? But I don't complete the next one, so I have 1 plus half. 1 plus half give me these 3 halves that you're seeing here. Okay, so all this to say, this is not good. These squares are not fitting properly. So all this to say that I'm trying to write equations for these different wavelengths and for these different frequencies of these standing waves. And just by observing it, I got to the conclusion that, let's write this down. The first harmonic has a certain frequency, which I'm going to call the frequency 1. Okay, index 1 to remind me that this is the first harmonic. And for the first harmonic, what I see is that the whole length of the rope gives us not even a whole complete wavelength, but just half of it. Okay, let me go for the second harmonic. What did we conclude about the second harmonic? Well, the frequency of the second harmonic is larger than from the first harmonic, and in fact, the frequency for the second harmonic is twice the frequency of the first harmonic. Okay? And what else do we see? Well, for the second harmonic, we did complete a whole wavelength. I'm going to put this index 2 here. So the whole length of my rope gave us a whole wavelength. Okay, let's continue. Third harmonic. For the third harmonic, the frequency is even larger than the second, even larger than the first. So the third harmonic, the frequency for the third harmonic is 3 times the frequency of the first one. And what do we see? Well, we looked at the whole length of the rope, we watched this standing wave, and we concluded that we have a whole wavelength and half of one more. 1/2 plus 1 gives me 3/2. And I'll say that this is 3/2 of the wavelength for the third harmonic. And we can keep going on with this if you want. We can put one more here. The fourth harmonic. So the fourth harmonic will be the frequency 4. This 4 is just an index, which is 4 times the first harmonic. And the L here, well, now you can anticipate. What does it look like? We are going half and half, right? Here I had half. Here I had 2/2 give me 1. Here I have 3/2. So here I will have 4/2, which will give me twice the wavelength with this index 4. And this thing goes on. Okay? So by watching this, by playing a little bit with this, we can try to get a general equation for the wavelength of these standing waves. Okay? So this is what is showing up in this next slide. We just by looking at each one of these standing waves, we can arrive at this equation here. Let's see how they did this, starting from this one on top. Look, 1/2, 2/2, 3/2, 4/2. So we conclude that the length of my rope is equal to n times the wavelength of that harmonic n divided by 2. Okay? So this is my general expression that covers all of these ones that we talked about. 1/2, 2/2, 3/2, 4/2, and so on. So n is a natural number. Now it's 1, 2, 3, 4, and so on. Okay, so from this equation, now I can write it in terms of the wavelength directly. I say, look, now I have the wavelength for any harmonic. The wavelength for any harmonic is given by twice L divided by N. This is the equation that you see on the slide showing up here. Okay, so let me put this in red. Let me make a nice square here. This is an important equation what we found. So this equation is telling us what are the possible wavelengths for standing waves. For standing waves where I have this rope fixed here, right? The rope fixed on both edges. So what are all the possible wavelengths that I can have? Well, here we are. Wavelength for the first harmonic is covered by this equation, for the second, for the third, and so on. All I have to do is to change the value of n, and I can get the wavelength for any of these standing waves. Okay, I have now the wavelength for any of the harmonics. I can also get the frequency. See, the medium of propagation is always the same, it's always that rope of length L with the same density, with the same tension. So the wave is propagating with the same speed. So the speed is not going to change. So with this in mind, I can now get an expression for the frequency. Okay, so let me write this down. The speed for that particular wave or for that particular rope that has that fixed tension, fixed density is constant. Okay, so the speed there is constant. I found an equation for the wavelength, so I can use the expression for the wave velocity to find now an expression for the frequency. So what we know that the wave velocity is the wavelength multiplied by the frequency. All right, what we have is then the wavelength is the wave velocity is the wavelength that we found, and that is 2L divided by N. No? So this is the wavelength for each one of my standing waves multiplied by the frequency. I'm putting this little index here because each harmonic has a different frequency. Okay, so from here, I found now an equation for the frequency for each one of those possible harmonics. The equation is n is a natural number, 1, 2, 3, 4, and so on, multiplied by the speed of what? The speed of the wave in that particular rope that we are playing with, divided by 2L. Okay, so let me put this one also in red. We now found an equation for the frequencies of the standing waves. What we also know is that the frequency increases as I go from first to second, from second to third harmonic. And how does it increase? As I said here, the second harmonic is twice the first. The third harmonic is 3 times the first. So this equation that I wrote here, I can also say that this frequency of the nth harmonic is n times the frequency of the first harmonic. Okay, okay, so all this is in this slide. Let me just summarize. By looking at each one of these standing waves, I was able to find an equation for the wavelength of each harmonic n. First is n1, second is n2, third is n3, and so on. And by knowing that the speed does not change because my rope is always the same, I was also able to find an equation for the frequency of each harmonic. Okay, and I also know that the frequency of each harmonic increases as I go down in the harmonic. Now, if I go from first to second, second to third, so this equation that I wrote is also equal to n, the frequency of the first harmonic. Okay, so these are two very important equations that will be showing up in other problems that we'll solve also in chapter 12. Now let's just try to solve a single problem, not too hard. So we are going to need these equations that we just derived, and that other one that I told you that will always be given to you if you need, which gives the speed of the wave in terms of the tension of the rope and the density in this medium. Okay, so let's see what is the problem asking us. We have a piano string. Okay, they give us the length, so let's write down this length. The length of this piano string is 1.10 meters. Okay, it has the mass of 9 grams. Okay, careful with the units, right? Put it in kilograms, so multiply by 10 to minus 3 kilogram. And they come with the question, how much tension must the string be under it if it is to vibrate at a fundamental frequency of 131 hertz? So just by reading this problem, we know that they are giving us this frequency of the fundamental, which is the first harmonic. That's why I'm putting this index 1 here, which is equal to 131 hertz. All right, what is the first question? What is the tension? Okay, so how are we going to do this problem? Let's try to put all the equations that come to our minds, okay? Well, I have an equation for the first harmonic, for the fundamental, in terms of the speed and the wavelength. And this is the equation that you see here, right? If I put F1, I have 1 speed divided by 2L. Okay, so I'm going to write this. Frequency of the first harmonic is V, the speed, divided by 2L. All right, I have this frequency, I have L. With this equation, I can find the speed. The speed for the wave to propagate in this medium. How can this help me? Well, the question is the tension. What they want to know is this tension here. Well, I have also that other equation that is given to us here. Let's copy it here, that the speed is the square root of the tension divided by the mass divided by L. So this is very good. I found V in this equation. I can put the value of V here. M is given to me, L is given to me, and so now I can find the tension force that they were asking. So we are done with the first question of the problem. Let's have a look at the second. What are the frequencies of the first 4 harmonics? This is very easy because the frequencies just go on increasing. So the question B is, what is the frequency of the first harmonic, the second harmonic, the third harmonic, the fourth harmonic? Well, the first one is given to me, 131 hertz. Nothing else to do here. What is the second? Just multiply the first by 2. What is the third? Multiply by 3. What is the fourth? Multiply by 4. And you could go on. Okay, so then you have the numbers here, 131, 262, and so on. All right, so this is the end of this chapter.